So welcome back. We will have our next speaker, Victor from Umea, telling us something about the geometry of a random right-angled Coxeter group.
Yeah, thank you very much, and thanks for the invitation for organizing this very nice workshop. Okay, so I'm going to speak about, I'm going to speak about something I've been working on for a few years with a variety of co-authors. So primarily Jason Berhstock, who's over here, in New York. More recently, my PhD student Altar, who's with me in Umea, and also two other group theorists. So Mark Hagen, who's now in Bristol, and Tim Suss, who's at Simon's Rock in the States. And yes, so for combinatorialists, including myself, there are some sort of somewhat scary words in my title. So I'm claiming that we'll be speaking about the geometry of random right-angled Coxeter groups. So the truth is, the only word in this title I'm really truly comfortable with is random. I don't know that much about the geometry of right-angled Coxeter groups. I've been picking up a few things over the years, but this is I'll definitely be skating over thin ice in the first part of this talk when I'll be trying to explain what all of that means concretely. But thankfully, I'll be able to cast the questions I'm interested in terms of graphs and random graphs, and then there'll be some nice problems, including, I think, a nice open problem that I will leave you with at the end. So you bear with me in the first half of the talk, and then we'll get onto the random graph theory. Okay, and I should also maybe say something about the history of this project. So this started a few years ago, quite a few years ago now. It was about a week before my third of my children was born. I was in my office in Vanderbilt, where I was an assistant professor at the time. And someone knocks on my door, and I see this unknown person with a beard. And in States, you're always a little bit nervous, and they might have a gun. But this person just says, "Do you know about graphs?" And I say, "Oh, well, maybe a little bit." And then we start talking, and turns out this person is a group theorist. This is, in fact, Jason. And he was visiting Vanderbilt to give a talk in the geometry group theory seminar. But he had some question about graphs and random graphs, and he asked some questions into his audience, knocked on a few doors, and eventually end up in my office. And we start talking. At first, there are a few cultural differences because he insists that G is a group and graphs are gamma. And at first, this is a bit hard, but I eventually understand what he's going on about, and that he has a very nice problem about random graphs lurking behind his questions. And we start working on it. It's the beginning of a beautiful collaboration, a beautiful friendship. And so, I guess, in the deference to him, I will use gamma to denote graphs throughout this talk. Okay, but having given you the background story, let me tell you about Coxeter groups. So let me start skating on thin ice. What's a Coxeter group? That's a group where you have it has a presentation of the following form. You have a bunch of generators, V, and then you have some relations. So first, all of your generators are involutions. They have order 2. So if I take V squared, that's always going to give me the identity for every generator V in my set of generators. And additionally, I may have some other relations. So if V and V prime are two different generators, then it may be that there's some integer greater or equal to 2, such that VV prime raised to that integer power is the identity. And for all pairs of generators, I have no finite relation, in which case I just let MVV prime be infinity. Okay. And in this talk, I will focus actually on a special class of Coxeter groups known as right-angled Coxeter groups. So I'll explain the next slide where this word right angle comes from. But right-angled Coxeter groups are really nice and simple. So all of the generators are involution. They have order 2. And then you have some pairs of generators, a VV prime, which commutes. That means that their MVV prime is equal to 2. So if MVV prime is equal to 2, that means that, and V and V prime are both involutions, this just means that V and V prime commute. VV prime, same thing as V prime V. Okay, and the rest, they have no finite relations. Right. So one of the nice things about right-angled Coxeter groups is you can present them using graphs, or represent them using graphs, I should say. So the right-angled Coxeter group W gamma, presented by the graph gamma equals VE, that's the right-angled Coxeter group, which has generators V, and again, you have involution, so order 2 generators. So MVV equals to 1 for every one of my generators V, which means that they're V squared equal to the identity. And then you have some pairs of generators which commute, and the rest I just have no finite relation. Okay. And by results from Muller in the 90s, there's a bijective correspondence between gamma and W gamma, so you don't have to worry about alternate ways of alternate choices of generators for a random right-angle Coxeter group. You can just work with the graph gamma and you've lost nothing. So this is what we'll be focused on in this talk. So where do Coxeter groups come from, and where does this word right angle come from? Well, Coxeter groups were introduced by the geometer Coxeter in the 1930s, and they're an abstract generalization of reflection groups. So here's a very hand-wavy picture to try to convince you of why this might be. Imagine you have two reflections. Well, you have a bunch of reflections in some geometric space. So reflections are involutions, right? You reflect with respect to a hyperplane and reflect again, you're back where you started from. So all of your generators are involution. And then if you have, say, reflection with respect to, for example, two lines which meet at a nice angle. So here I have lines L1 and L2 meeting an angle pi over 4. And you first reflect with respect to L1, then L2, then do that again, and again. After an integer number of times, you're back where you started from. So somehow Coxeter groups are a kind of abstraction of reflection groups, and they have the same sort of properties. And if you have two hyperplanes which are mutually orthogonal, then actually reflection with respect to them commutes. This is where the right angle comes from in right angle Coxeter groups, right? So if I have lines L1 and L2, which are at right angle to each other, and I first reflect with respect to L1 and then L2, that's the same thing as reflecting with respect to L1 and then L2. So right-angle Coxeter groups are somehow an abstract generalization of reflection groups where some of the generators are mutually orthogonal and the rest are completely unrelated and have no finite relation evaluating the identity. Okay, so those are right-angle Coxeter groups. So why do we care about them? Well, okay, I guess I care about them because Jason cares about them, and Jason cares about them because right-angle Coxeter groups, so RACGs, they play a fundamental role in geometric group theory. A lot of other groups can basically be embedded inside right-angle Coxeter groups. So they're a very interesting, a very rich class of examples as far as they're concerned. And geometric group theory, as far as I can work out, is greatly concerned with the study of the large-scale geometric properties of Cayley graphs of a group when equipped with the graph distance metric. So here I'm being a little bit vague. So usually when we think of Cayley graphs, we have to specify a set of generators. But it turns out that geometric group theorists care about the kind of properties which are not affected by the choice of generators. So I'll just be a little bit vague. And just to make sure that we're all on the same page, let me give an example of a Cayley graph of a nice right-angle Coxeter group. So suppose I have a right-angle Coxeter group which is presented by this graph gamma. We have three generators, A, B, and C, no relationship between them. Okay, so then I can just start generating more elements of this group using these generators. So if I start from the identity, I can generate B, BA, BAB, BAC, BC, and so on, or A, AB, AC. And if I just keep going in this way, I will generate a tree. And so the edges correspond to multiplication by one of my generators. And since I have no relation between my generators, apart from the fact that each of them is an involution, I would just generate this infinite three-regular tree, also known as a Bethe lattice. So this is what its Cayley graph might look like in this case. And here's a different example, which will also be relevant to what we'll be discussing later. Now the presentation graph, my right-angle Coxeter group is a square, an induced four-cycle. So I've drawn it as a K22, but it's a square, right? You have two diagonals, A, B, and C, D. Okay, so what kind of Cayley graph does that have? Well, A and B don't commute. And so they give me a kind of infinite line, right? Starting from the identity, I have A, AB, ABA, ABAB, and so on and so forth. And of course, also have B, BA, BAB. And similarly, C and D don't commute. So I have a kind of horizontal line here, DC, D, identity, C, CD, CDC, CD, 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 and so on and so forth. But because I have all these relations across, when I take the K graph of the whole structure, not just of the subgroups generated by AB or by CD, I'm going to get the square integer lattice. Indeed, because A and D commute, I have this edge here, I have that AD and DA are the same element. So here, this is AD, but I could also have written DA. This is the same element because A and D commute. And so there I'll have this nice square integer lattice as my Cayley graph. So the reason I've shown you these two examples, well, it's partly to illustrate what the Cayley graphs are about, but also these two examples exemplify two extremes in terms of the geometric properties of Cayley graphs. Broadly speaking, well, they have very different divergence, and so divergence is apparently a fundamental notion in geometry group theory. So tell me all the three geometry group theorists I've talked with. It has a slightly finicky definition, but the basic principle is the basic principle is fairly simple. So imagine you have 3 points x, y, and z in a metric space, and y is sort of somehow the halfway point on the geodesic from x to z. Then just take out a ball of radius proportional to the distance between x and z around y, and measure now how long the shortest path between x and z is in what remains of your space. So how long is the detour you have to make if you have to avoid y? Like if you have to stay far away from y. And so how much you have to divert from your path to avoid kind of a hole some in your space. And the thing that geometry group theorists really care about is the growth rate of this function as the distance between your initial points x and z grows. So there are some sort of scary words like quasi-isometry invariance. Let me maybe not focus on the geometry group theoretic details here, but just show some picture that really illustrates what this is about in these two extreme cases. So if you go back to the Cayley graph I had shown you of the right-angled Coxeter group generated by the empty graph on 3 vertices, that has infinite divergence, because if I take x and z and then cut out y and anything around y, then I'm suddenly going to disconnect the graph, right? This is an infinite tree. Suddenly x and z are sitting in different components. There's no way I can get from x to z. So this is somehow an extreme case. If I destroy something along a geodesic, then suddenly the length of the shortest path in what's left has become infinite, or well, then there's no shortest path, no path whatsoever. At the other extreme, you have the second picture I had shown you, where you have the square integer lattice, and you can imagine if I have 2 points x and z sitting on a chunk of the square integer lattice, and I take out not only y but maybe some ball around y, like this inside this blue pyramid. I take everything out. I take out everything in there. Well, I can still get from x to z. I just have to take a little detour, but I eventually get back to where I started from. And basically, you can easily convince yourself that no matter how far, no matter how I choose x and z, if they're far apart, I will never, even if I take out almost everything in the geodesic between them, and quite a few points are close to the geodesic, I will still have some path of length basically proportional to the length between x and z from x to z. So I can take out large holes and still my space is well connected. So there's these two extremes of kind of infinite divergence in one case and linear divergence. They exemplify kind of dichotomy that geometry group theorists care a lot about. On the one hand, you have hyperbolicity, which I'm not going to define, but which was introduced by Gromov in the 90s, where you have this is the property of groups whose Cayley graphs are tree-like. And you also have the related notion of relative hyperbolicity, which was introduced by Gromov and developed further by Fard. So this is a group which is it's not quite hyperbolic, because it might have some non-hyperbolic subgroup or patches. So you think of it like you have a huge space, and maybe locally you have some patches that are not quite hyperbolic. But if you kind of stare at it from very far away, the non-hyperbolic bits aren't kind of glued together in a nice way. So over long distances, you still look hyperbolic. That's this concept of relative hyperbolicity. which means that the non-hyperbolicity is confined somehow to subgroups that do not interact with each other in a substantial way. So that's at the one extreme. These are things which are more like this, whose Cayley graphs. These are groups whose Cayley graphs looks more like the Bethe lattice, the infinite three regular tree. And at the other end, you have well, thick groups. So algebraic thickness was a notion in group theory, which was introduced by Berhstock, Grutu, and Mosher. And it's if a group is algebraically thick, that gives you some bound on its divergence. And in particular, being thick is an obstruction to relative hyperbolicity. So it tells you you're not in this relatively hyperbolic world. So results of Berhstock, Hagen, Sisto, and Lefkowitz together imply, in particular, that you have a group, right-angle Coxeter group, W gamma, which is thick of order k, then its divergence is polynomial of degree k plus 1. And there's a general dichotomy for right-angle Coxeter groups. You're either thick or you're relatively hyperbolic. And these are the two worlds, and the divergence allows you to tell these two apart. As soon as you're relatively hyperbolic, your divergence is exponential. Okay. And so this is a very important dichotomy, and group theorists are interested in examples of interesting groups with either of those properties. And the natural question which comes up is, okay, what if you take some random groups? What can you say about their geometric properties? So already Gromov had a nice random representation model where he generated groups with by taking n generators. And then each word of length n, which he could build with those n generators, would evaluate to identity with probability p independently at random. So you have these, you randomly add relations that evaluate to the identity. And this model was analyzed, and there are some interesting things which have been done with it. So regarding to our discussion, I suppose I should say that as the length of the relations that you're allowing to evaluate to identity tends to infinity, and if p is fixed, you fall into one of two worlds. Either you're in the hyperbolic world, asymptotically almost surely, or in fact your group collapses to something finite, asymptotically almost surely, and the tradition occurs at a half. So you can basically generate two different types of examples using Gromov's model. More recently, Charney and Farber introduced a model of random right-angle Coxeter groups. And here they leverage the fact that these right-angle Coxeter groups can be basically described entirely in terms of their presentation graph gamma, right? So gamma was a graph which tells you which generators commute, and all generators have order 2. And so they said, well, why don't you take gamma to be the Erdős-Rényi random graph, right? You have n generators, and you let any pair of generators commute with probability p independently at random. Okay, right. And here they observe that you get some, well, different behavior, at least to that's seen in the Gromov random representation model. For instance, they show that if you contain an induced square, an induced force cycle in your graph gamma, then the group you generate in this way, the right-angle Coxeter group you generate, W gamma, has to be infinite and not hyperbolic. Infinite because, as we saw, the subgroup induced by the subgroup generated by an induced square has as its Cayley graph the square integer lattice. That gives you infinity for free, and it also tells you you're not hyperbolic because you have this big non-hyperbolic patch somewhere in your graph. But as I mentioned, I mean, this could be a purely local patch, right? If you imagine you have a few squares, but they don't really interact with each other in a meaningful way. So the interesting question isn't whether you're hyperbolic or not for these random right-angle Coxeter groups. It's whether you're relatively hyperbolic or not. Whether these patches of non-hyperbolicity somehow can be glued together to make the overall space non-hyperbolic. And that's a question that I've been working on for a few years. So recently with Jason and my student Altar, we proved we almost get the threshold for relative hyperbolicity in this random right-angle Coxeter group model. So again, the presentation graph for your right-angle Coxeter group is GNP. And then if P is a little bit below 1 over square root n, we can show that W gamma is asymptotically almost surely relatively hyperbolic. And if you're above a certain constant over square root 10, then in fact you're almost asymptotically almost surely not relatively hyperbolic. So something happens at around 1 over square root 10. In fact, we can say a little bit more, something a little bit more precise. So improving earlier work with Hagen, Suss, and Berhstock, together with Tim Suss and Jason Berhstock, we could show that the threshold for quadratic divergence occurs roughly at square root of 6 minus 2 over square root of n, which feels like a bizarre number. So in the time that I have left, maybe I can try to explain a little bit how these results are proved, and then leave you with an open problem. So yeah, 10 minutes. Good. So let's start with the second theorem, right? And I should say that this theorem one is the one that basically allows us to show that you're not relatively hyperbolic above 1 over square root 10. So you can think of this as the upper bound. Basically, above this value of p, we can control the divergence in the right-angled Coxeter group quite effectively. And how do we do this? Well, we do this by studying what is known as the square graph. So given a graph gamma, we construct an auxiliary square graph whose vertices are the non-edges of gamma, and whose edges correspond to those pairs of non-edges that together induce a square or a full cycle in gamma. So here maybe a picture's worth 1,000 words. On your left, you have a graph gamma, and on the right, you have its square graph. So for example, inside this red circle here, you can see I clearly have an induced square that corresponds to an edge in my square graph, right, between the diagonals 2, 4, and 3, 5, non-edges. Inside this blue patch here, there are several squares. So 5, 6 induces a square with 2, 7, and 2, 8. I have those two edges. And then I think 2, 7 also induces a square with 1, 6, and 1, 5. So you have these two edges. And here, if you look at 5, 6, 7, 8, I do have a full cycle, but it's not induced. I don't see anything with sort of 7, 8 in my square graph. And then all of the other non-edges, and there are a few, they're not involved in any square graphs. They're just isolated vertices in square of gamma. Okay. So I'll write this in a minute, but I'll just say already now that I'll refer to the non-trivial components in my square graph as square components of my original graph. And for each square component, there's a set of vertices that it lives in, that it lives on, right? So for example, this square component here lives inside this red set of vertices, and this component here lives inside this blue set of vertices. And I'll refer to these sets as the supports of my square components. And I immediately note that these don't have to be disjoint at all, right? So two different or distinct square components could perfectly well live on the same set of vertices. Okay. So here I've just written this in words. Non-trivial square components of the square graph are square components, and supports, that's just the collection of vertices they live on. Right. So now let me talk about the properties of the square graph of gamma when gamma is an Erdős random graph, and this is something we refer to as square percolation. And here, let me again stress that this is induced square percolation. I don't care about full cycles which are not induced. I only want the induced squares. Okay. So for the upper bound, one thing which we used was the result of Danny and Thomas from 2015. So they showed that if you have a right-angled Coxeter group which is thick over order 1, then that happens if and only if its presentation in graph gamma has a square component with full support. So it lives in the entire set of vertices. And this is intuitively telling you that you have a way of stitching these squares, which are not hyperbolic, together to cover the entire group. So somehow this controls the overall geometry of the Cayley graph. So this is why you're not relatively hyperbolic. So equipped with this result, to determine the threshold for quadratic divergence, we need to study square percolation. And unfortunately, this is a bit of a nasty model, right? So GNP is perfectly nice, but the square graph of an Erdős random graph is quite nasty. So to begin with, it behaves very badly with respect to addition and deletion of edges. When I add an edge to my graph gamma, potentially that creates new full cycles which use that edge, but it could also destroy some induced full cycles that I had before. When I add edges, I could create some things but destroy some things. And conversely, if I remove an edge, the same occurs. And there are also some difficulties with dependencies in the sense that you can have square components sharing edges but being distinct, sharing vertices and being distinct. And in fact, we, together with Alta and Jason, we even have examples of graphs gamma where you have three distinct square components which have full support but are distinct. So there are like three different ways of stringing together induced C4 to cover everything, but somehow these C4s don't meet in any way. So connectivity is going to be a bit weird, right? You can't think of two things being on the same space as being necessarily connected. Thankfully, we could, to study the square graph, we could use a very nice framework set up by Bella Bollebash and Oliver Jordan in the study of clique percolation. So clique percolation was a kind of hot topic in network science in the early 2000s after work of Rényi, Pal, and Vicek. Here you basically looked at cliques and random graphs, and you connected two cliques, to say 2K cliques, if they had at least S vertices in common, and you ask yourself, is there a giant component? And this was motivated by applications to community detection in networks. So Bollebash and Jordan had a very, very nice framework for studying these things. Unfortunately, it didn't work perfectly for us, but it was a very solid basis on which we could build. So the challenges I've alluded to led to some additional difficulties, but building on their work, we could determine the threshold for the emergence of a square component with full support with some precision. And this is what led to the upper bound in the relative hyperbolicity threshold. So if you remember, this upper bound was a form square root of 6 minus 2 over square root of n. So I won't give you the proof that this is the threshold for having a square component which covers everything, but I'd like to at least convince you this might be a reasonable guess as, for the emergence of at least of a giant square component, of a square component that's covering a pretty decent proportion of all squares. And the intuition is that you start from, you try to explore the square graph starting from some induced C4 with two non-edges f and f prime. And then you look at the common neighbors of the vertices in f outside the C4. So this is set x, and this is the size of it is distributed like a binomial random variable with parameters n minus 1 p squared, roughly binomial np squared. Okay. Now, if I have no edge between x and f prime, then any non-edge I can choose here is going to induce a C4 together with f. So the number of induced C4 I see in this picture is going to be size of x plus 2. These are these two extra vertices, choose 2, because any pair of them is going to give me a C4. But one of these C4s I already knew about, this one, so I need to subtract 1. So this is the number of new C4s, the number of new non-edges that I could use to explore further. Now, obviously, I care a lot about the fact that this is an independent set. And then, if if you look at this number and take p to be lambda over square root of n, you can see that the expected number of new C4s I'm kind of discovering in this way is an expectation lambda to the 4 over 2 plus 2 lambda squared plus the low of 1. And basically, if you solve lambda to the 4 over 2 plus 2 lambda squared equal to 1, you get this strange number, square root of 6 minus 2. So I guess the upper bound result is kind of making rigorous the intuition that the moment at which this exploration process seems to have a good chance of discovering more than one new C4 per step is the moment when you can hope to, well, you see a giant square component emerge. And now, obviously, you still have some work to do because you somehow need to ensure your square component covers everything, and you have lots of dependencies to handle. But this is at least giving you some intuition for the results. Okay, and I'm almost out of time, so let me very quickly just say a few words about the low bound, which is actually, I think, quite interesting because this is where the open problem is. So what we use is basically a translation from algebraic thickness, which is a property of groups, to a graph theoretic property of thickness. And sort of fairly technical notion. So let me just try to quickly give you some sense of how you define thick graphs. You say the graph is thick of order 0 if it's if there's a bipartition to two sets A and B, so that you have all edges present between A and B, and you have at least one non-edge in A and one non-edge in B. And then your thick of order 0 components will be the collection of all non-edges you see in this picture. All non-edges inside A and all non-edges inside B. And then once you have these, you can use them as building blocks for general thickness. So that is, you have a thick of order at most k piece. So you have two thick of an order at most k piece, say this one and that one. And there's a non-edge living in the intersection of the supports. Then at level k+1, you can merge them together. Where you can merge these two together and these two and these two. And maybe here there's a clique and you can't merge them, but maybe this one attaches to that one because of the non-edge intersection of the supports. And in addition, you can also beam up cherries. So you have a single vertex which hits a non-edge in the support of some level at most k component. You can also add that. And once you've done this merging, you have a new level k+1 component, and it has a new support, a bigger support. And this gives you lots of new non-edges you can use to merge other things, to latch on to use as latches for other components. For example, this non-edge is now accessible to glue another component, and this non-edge and this non-edge and so on. So you can use all these non-edges to glue order k+1 components and get an order k+2 and so on and so forth. And your graph is thick is a way of doing this gluing process and eventually covering all the vertices. And the key to, and I think it will basically end up with this. So the key to our lower bound result is that we have an extremal bound for thick graphs. We show that if a graph is thick, if you can glue all these thick pieces together to cover the entire world eventually, then you need to have at least twice the number of vertices minus 4 edges. And there are many extremal examples for taking this bound. Complete bipartite graph with 2 vertices on one side, a bunch of induced squares glued together, or in fact any tight example as long as you glue them alongside a non-edge. So there's a fairly involved inductive proof of the statement. But using this theorem, we can show that there are no large thick pieces in gamma when p is a little bit below 1 over square root n, because basically sets of size order log n don't have enough edges at that density to support a thick component. It's a very crude bound, but this is what helps us to prove our low bound. And so maybe I will now leave you with the obvious open problem. In the theorem I showed you, the low bound, the threshold at which we could guarantee relative hyperbolicity was of order 1 over square root n log n, but the log n shouldn't be necessary. So there should be some clever way of using the structure in thick graphs to improve the bounds, but we were not able to do that yet. And then I guess the second question I could ask is about the size of the second largest square component once the giant square component emerges, because we haven't quite got a handle on that, at least right at the thresholds. But maybe I'll just end with a more general admonition to go and talk to your friendly neighborhood group theorists, because it turns out they actually have some very nice problems about random graphs lurking under the group theoretic jargon. Thank you very much for your time.